I'm going to start off by saying that I believe this is going to be probably the most watched video, if not for now, then for the entire year. Because I think something that we've really struggled with, either at Marana Cook or with memorizing things and stuff like that, is really internalizing trigonometry. And a lot of people hate it, and it's fine if you hate it, because in real life, you're not going to use it a bunch, but in physics, you are going to use it, which is why I'm going to be giving you a review. So, I'm going to break this review down into two parts. So, if you want to skip ahead, just look for this little circle in the top right corner. Part 1 is going to be special right triangles. The second part is going to be trig functions. Why, might you ask, am I talking about special right triangles before trig functions if this video is on trigonometry? Well, it's going to be because in AP Physics, you are almost always going to be asked about special right triangles, and you are almost never going to be asked about more generalized angles. Now, Casey may ask you this, but it's probably not going to be on the AP exam. So that's why I want to really hit home special right triangles. All right, so there's two special right triangles that you're going to want to memorize. And you're going to want to remember that term, special right triangles, because if these angles are the same, then they are all going to be following this relationship. So the first one is a 45, 45, 90 triangle, which is going to look something like this. So 45 degrees, 45 degrees, and 90 degrees, which is indicated by that little square in the corner. So I'm going to write everything down in terms of one of the side lengths, A. So if you have A for one of your side lengths, this side length is also going to be A, and this side length is going to be A times the square root of 2. All right. Well, why is this the case? Well, if you remember from Pythagorean's theorem, a squared plus b squared equals c squared. In this case, both side lengths are a. So your last side length is going to be b squared, and b is going to be equal to, if you imagine combining them and taking the square root, a times the square root of 2. So that makes sense. Well, why do you care about special right triangles, not the Pythagorean theorem? Well, in this case, we don't even need to use the Pythagorean theorem at all. And the reason is because we've already know that these two side lengths are equal because of the special right triangle. If I didn't give you any of the side lengths, or if I gave you one, it can be hard to justify why two sides are equal. Even though we know intuitively that this side is equal to this side, if I don't give you any of those specific side lengths, it's often hard to draw direct relationships between them without using trigonometry, which we're trying to avoid, remember. All right. So that's the first kind of special right triangle. What about the second kind of special right triangle? Well, so it's going to be a 30, 60, 90 degree triangle. So this side's going to be 60 degrees. This side's going to be 30 degrees. And as always, I'm going to pick the shortest side to be the variable in question, which is going to be b. So here are what the side lengths are. This right side is going to be b. The hypotenuse is going to be 2b. And the long leg, that's a fancy way of saying things about a triangle, is going to be b times the square root of 3. All right. And again, you will never be asked to use trigonometry to solve these problems in 99% of cases. So special right triangles are the way to go. Because if you imagine b, if you are only given this side length b, and I asked you what these two side lengths were, you couldn't immediately use the Pythagorean theorem without at least knowing two of the sides, which is why we use special right triangles. And you can verify that these use the Pythagorean theorem, but that should be your own exercise because I'm confident that at least that has been taught thus far. All right, so these are your two special right triangles that you're going to want to memorize. Now I'm going to get on to the longer and more tedious part 2. So, general trigonometry. Let's do that. So, I'm going to give you a first glance overview of trig because that's all you're really going to need. And the first thing you're going to want to memorize is this little phrase. So ka, toa. So, ka, toa. So what does this phrase mean? Well, if you imagine drawing a right triangle, the angles do not have to be particularly accurate in this case because we're dealing with a general right triangle. And imagine you call one of the sides and you say that has an angle of theta. All right? And you want to find sine of theta, cosine of theta, and tangent of theta. Well, the S stands for sine, the C stands for cosine, and the T stands for tangent. All right. What do the O's and A's stand for, and H's? Well, A is going to stand for the side directly next to your angle theta. That is flat, not the hypotenuse. So, the leg of your triangle next to your angle. Repeat it. The side of your triangle that is not the hypotenuse next to your angle. Okay? The opposite side is going to be the side directly opposite your angle. So if you imagine drawing a straight line from the crux of your angle out into the side of the triangle, that is going to be your opposite side. And then your hypotenuse is always going to be your longest side, and it's going to be right there. All right, so now we know what the O's, A's, and H's stand for. Well, why this phrase? Well, this phrase is telling you how to relate these things to find sine. So, and cosine and tangent. So, sine of theta is going to be opposite over hypotenuse. Tangent of theta is going to be opposite over adjacent, and cosine of theta is going to be adjacent over hypotenuse. So that is what these little phrases mean here. So means sine is equal to opposite over hypotenuse, cosine adjacent hypotenuse, ka, tangent opposite adjacent, toa. Tangent is equal to opposite over adjacent. So I'll write this out explicitly if you don't want to use this mnemonic. Sine equals opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. And tangent is equal to opposite over adjacent. All right. So this is the most bare bones glance that you can take to do this. So now I'm going to get into a little bit more nitty-gritty of what you're going to need for physics. So I've shown you what these trig functions are, but how do we work with them? Well, I'm going to delete this for now, and I want you to refer to this little table up here, which is pretty much just a restatement of what I said in that phrase. So let's say I have a vector, and let's say it's in the xy plane, and I'm saying that I'm traveling 40 miles per hour, 30 degrees up from the x-axis. And I asked you to find different components of this. Well, the way you would do that is by solving for your hypotenuse sides, your opposite sides, and your adjacent sides. In this case, because we know the length of the vector, we know the hypotenuse. The hypotenuse, in this case, is 40 miles per hour. How do we find the adjacent side? Well, if we know hypotenuse and are trying to find adjacent, which of these three formulas should we use? Well, the formula we should use is cosine, right? Which is equal to adjacent over hypotenuse. So in this case, cosine of 30 degrees times 40 miles per hour is equal to this component of our vector. Because if you imagine drawing a triangle, we're solving for this leg of the triangle. So that component, which in this case is the x component. So this is equal to the x component of our vector. But wait, cosine of 30 is just square root 3 over 2, right? And if you remember from our special right triangles, this is 2 times this side, so this side would be 20. And this side is going to be 20 times square root 3, so 20 square root 3 miles per hour. So again, this is why you might want to use special right triangles instead of trig. But if you have to use trig, I'm going to return back to this. So if you plug this into your calculator, you'll find that cosine of 30 is going to be square root 3 over 2. So distributing the 2 down to the 40, this is going to give you 20 square root 3 miles per hour for the x component of this vector. What about the y component? What about this component right here? Well, if you remember, we need to use a formula from this list right here that we know the hypotenuse, but we don't know the opposite side, which sine is going to be our option in this case. So, to cancel out the hypotenuse in the denominator, just like we did earlier, we're going to take sine of 30 multiplied by the hypotenuse, 40 miles per hour, and that's going to give us our y component, which, again, you could use special right triangles for, or you could plug it into your calculator and find that sine of 30 is 1 over 2. So 1 over 2 times 40 miles per hour, we find that the y component is 20 miles per hour. And just like this, we have now used trigonometry to find different components of vectors, which is something that I cannot stress enough. You will be using this a lot in physics. So try working through this example again, step by step, without my instruction, and see if you arrive at the same answers, either using a calculator or using special right triangles. Either way, this is something you need to know. Now, I'm going to talk about one last thing, which, if you are already overwhelmed, don't be worried. This is not something that's nearly as important, but something that you may be asked at some point. Okay, so imagine instead you are told the components of your vector, and you are being asked to find the magnitude of that vector and the angle of that vector. So if you imagine we draw on the xy coordinate plane, and I said you're traveling 3 miles per hour in the x direction and 4 miles per hour in the y direction. And I asked you, what is the angle of this vector that represents your total movement, and what is the angle? So what is the angle and what is the magnitude? Well, we can do this by using the Pythagorean theorem and by using arc trigonometry or inverse trigonometry, which you may have otherwise heard it as. So Pythagorean theorem, you should likely remember by now. So 3 squared, so a squared, plus b squared, so 4 squared, is equal to this side squared, so h squared. I'm just going to write h squared because we're dealing with trig notation, so I'm going to use AOH. So this is 9 plus 16 is equal to h squared. H squared equals 25. Because h is positive, we know h is equal to 5. All right, so now we know that this side length that I've labeled as h is actually equal to 5. All right, so 5 miles per hour, that is. So that is the length of our vector. Don't get this confused with a triangle. We're using triangles to solve for these angles, but the total length of our vector is 5 miles per hour. But in what direction? Because remember, vectors have directions and magnitude. So what direction are we pointing in? Well, this is where we use inverse trigonometry. So tangent of theta is equal to opposite over hypotenuse, right? So in this case, it's going to be 4 over 3. So 4 over 3. So we now have tangent of theta is equal to 4 over 3. Alternatively, you could have also used sine. So you could have said sine of theta is equal to opposite over hypotenuse, which you might want to think about for a second, but opposite is 4, hypotenuse is 5, or cosine of theta, which would give 3 over 5. So using any of these 3 trig functions, how do we solve for theta? Well, what you're going to want to do is you're going to want to take the inverse trig functions. So, pulling this formula down here, you're going to want to take the inverse tangent, or arctangent, of both sides, like this. Remember, if we're doing it to both sides of the equation, it'll still hold true. These will cancel, and then we'll have theta is equal to the inverse tangent of 4 over 3. Or alternatively, you could have used sine and cosine. So you could have had theta is equal to the sine of 4 over 5, and theta is equal to the cosine inverse of 3 over 5. And again, because we're using trigonometry and trigonometric relationships, these will all give the same angular value for theta, because we are solving for the same side. So you might want to plug this into a calculator and write this as your final answer. But the moral of the story is, this is going to tell you the angle of your vector, whereas the Pythagorean theorem will help you find the magnitude of your vector. So if there are a few things you take away from this video, have it be how to find the direction of a vector given two sides or two components. SOHCAHTOA, that's the big one, and special right triangles, another big one. Not every triangle is going to be a special right triangle, so that's why you need to use trig. But when there are special right triangles, it makes your life a lot easier. This has been a very long video, and I'm sorry if I made any mistakes in pronunciation. I hope they can be forgiven, because I really think this is important for people to know, and try my best to make good explanations. Alright, that's it. Hope you enjoyed.